Good afternoon, everyone. Today we will be presenting a project titled Safety Function Based Control of Transient Chaos in Discrete Maps. Myself, Anushka, and our team members are Marin and Nandita under the guidance of Dr. Shishishankar Mani. This project explores how machine learning, especially transformers, can help control chaotic behavior in nonlinear systems using safety functions. What the paper proposes. The reference paper we based our work on used machine learning to control transient chaos in the Lorentz system. It introduced the concept of a safety function, which represents the minimum control needed to keep the system stable. A transformer model was used to predict the system function directly from the data, removing the need for heavy computation. We built on this concept by implementing both classical and ML-based approaches for comparison. The transformer-based method proved to be much faster and more tolerant to noise. Our work. In our project, we extended the idea to multiple chaotic systems, the Lorentz, logistic, and Henon maps. We applied both classical and transformer-based safety function estimation for the Lorentz system. For all three systems, we simulated them under different noise levels to study how noise affects chaos, safety, and control. We analyzed how the safety function changes with increasing noise and how effectively it can maintain system stability. Importance of controlling transient chaos. Transient chaos is a temporary chaotic behavior that appears before a system becomes stable. It occurs in real-world systems such as electrical circuits, weather models, and even biological processes. Controlling it helps improve system performance, predictability, and stability. By using safety functions and machine learning, we can apply just enough control to keep a system operating safely without overcorrecting. This makes our approach efficient and ideal for noise-resistant designs. The Lorentz system. The Lorentz system is a classic example of chaotic defined by three nonlinear equations as shown. We use standard parameters sigma equal to 10, b equal to 8 by 3, and r equal to 20. To make it easier to analyze, we added small Gaussian noise and used a Poincare section at z equal to 20, which reduces the 3D system into a simpler 1D Lorentz map. This map relates successive crossings from yn to yn plus 1 and helps us estimate how control can stabilize the system. Classical computation of safety functions. The classical approach computes the safety function by dividing the region into many grid points and testing all possible disturbances. It keeps updating control values iteratively until it converges to the minimum control needed to keep trajectories safe. Although this approach is accurate, it's slow and computationally expensive, especially when noise and system size increase. ML-based safety function. Here, instead of manual computation, we trained a transformer-based model using 1D Lorentz map data. The model learned to predict the safety function directly from data. We then compared the predicted results to the classical ones and found them very similar. But the ML model worked much faster and adapted better to noise. Results and analysis. We compared classical and ML-based safety functions under two noise levels, eta is equal to 0.01 and eta equal to 0.1. Both methods produced almost the same result at low noise, but as noise increased, the ML-based model showed better adaptability and faster computation. This proved that transformers can provide a data-driven and efficient alternative for chaos control. Logistic map and effect of noise. The logistic map is a simple one-dimensional system that can exhibit chaos for certain parameter values. At r equal to 3.8, it becomes fully chaotic. We tested three noise levels 0.005, 0.01, and 0.1 and observed that as noise increases, the clear parabolic structure becomes more distorted. Eventually, chaos turns into random, unpredictable behavior. Interpretation of noise effects and safety function. This slide shows how noise affects both the logistic map and its safety function. At low noise, the safety function is well defined, meaning control is easy. As noise increases, the safety function flattens, indicating that the system becomes unstable and harder to control. This transition from deterministic chaos to stochastic behavior is clearly visible in the plots. Henon map. The Henon map is a two-dimensional chaotic system defined by two equations with parameters a equal to 1.4 and b equal to 0.3. We added Gaussian noise and analyzed its effect for noise levels 0.01 and zero point 0.1. As noise increases, the attractor's smooth folded structure becomes distorted, showing a loss of chaotic order and controllability. Safety function analysis and observations. Here we see the computed safety functions for the Hannon map within the region Q equal to -2 1.2, 1.2. At low noise, the safety function is smooth, meaning the system can be controlled effectively. At high noise, it becomes irregular, showing that more controlled effort is required and the system becomes less predictable. This pattern is consistent across all maps studied. In conclusion, the study examined how stochastic noise affects chaotic systems and how safety functions can quantify and control their stability. As noise intensity increases, the chaotic structure of the logistic and Hannon maps deteriorates, reducing predictability and increasing control effort. The safety function framework, supported by machine learning, effectively identifies and stabilizes chaos, enabling robust control of noise dynamical systems. Thank you.